My name is Mayank Yadav. I'm a third-year PhD student under Professor Mayank Yadav. This work has been already shown to the IPS 2025. This suggests the proposal to achieve the ultimate holding voltage tunability for SCR for wide range of PSD protection application with the assistance of Dr. Mayank Yadav. The outline of this presentation is into the flow, such as it touched a little bit of the basics of ESD and the importance of holding voltage and the tunability of holding voltage. It's outline for this presentation, just like some introduction of the ESD and the importance of holding voltage and how the holding voltage tunability has been achieved in the SCR. The second is the introduction motivation to validate the motivation to tunability of holding voltage has come into picture. Now the proposed structure that we have proposed to solve this problem. Further, RC trigger proposed structure to tunable little further to achieve this junction breakdown holding voltage and the trigger voltage tunability. I conclude in this next step, and the last I would like to present you the backstory of this proposed structure. Now the basics of ESD, as we all know that this is a high voltage, high current structure, that high current pulse that can disrupt the internal circuit that is basically parallel to the ESD clamps, and that clamps provide the protection to the internal circuitry. Now PMOS and NMOS are helpful for breakdown even further for ESD with the help of ESD clamp. Now if the gate oxide failure is the 8 voltage or the lesser than the 8 voltage, then trigger voltage should be below the 8 volts. Similarly, the 10 volts, if the gate oxide is too thick, then it should be the 10 volt of trigger voltage, and the latcher voltage would be the demand in the industry is always the greater than the latcher voltage. So in the picture, that holding voltage should be higher in the ESD shrinking window, and the trigger voltage should be lower. So as you see that this ESD window has been shrunken from higher the higher holding voltage, the lower than the lower trigger voltage. Right. If this the PN junction has been, I would like to give some overview of the SCR structure. The PN junction SCR structure coupled with two BJTs, that is PNP and NPN couples working in regenerative feedback mechanism. If the initial N tap to P tap, there is one IS1, that is reverse saturation current will flow initially with the anode and N tap has been zapped. After that, there is sufficient energy, the carriers from N well to P well has been carried out in this region. Biasing sufficient in this cathode region to a regenerative another mechanism that is called as holding state. Now the holding state is such that the latch up would not happen in the NPN and PNP regenerative well. Right. So this the holding voltage tunability importance is such that the fabrication is become very difficult if we want for the certain application. Suppose if you want 2 volts of holding voltage and 8 volts of trigger voltage, we need a specific dimension of the device. If we don't have the specific dimension, that we cannot proceed for the other application. Suppose if you, in the same chip, if you want the 3 volts of holding voltage and same the trigger voltage, that you cannot achieve by this dimensional change, by the dimensional change. You have to discrete this dimension with some of the parasitic performance, right? So after this, the problem has been solved by the motivation that is came to introducing few junctions into the NPN and PNP branches. Like here, the junction and NP is introduced in the emitter base series of emitter base, where the current is flowing in the reverse bias direction. Now the higher the input base current is being required to trigger or the current flow from IE to IE. Similarly happened with the this is PNP, and similarly happened with the NPN. So higher the base current, higher would be the voltage required to bias this NPN or PNP. Right. So the device proposal is such that we introduce the implants in the P well region, which is directly below the normal source drain implants. This implant, kindly note that this could not be higher implants, or we can say that normal source drain implant is the high energy, high dose, whereas the P plus is slightly lower dose implants, into the same region, which performs the NP junction over this P-well region. As you can see that here the diode is forming to support the parallel junction of the NPN, right? So I came up with this results later. First, we can see the equations that have been carried out after the TLP pulse over the anode and N-tap region. So if you see that the base emitter voltage is higher in the case of the diode potential, because the extra diode has been introduced here, and the supportive current that is already flown to the bulk region. Now, as a result, if you can derive this base current equation, and that is came across how the resistance, P-well and N-well resistance has been play a initial role to minimize the base current equation. Right. This base current equation has been reduced to, the base current has been, the smaller base current is required to trigger it for further regenerative feedback mechanism. In the contours of the TCAD, well-calibrated TCAD simulation, you can see that the current conduction happens from N-tap to cathode, and the cathode part has been vanished, or you can say the potential becomes zero. So the lower the conduction, the higher conduction and the lower on resistance has been carried out in this region. And please note that this at the same current density of 0.2 milliamperes per micrometer. Now, as the results came up, you can see that the TLP characteristics of the conventional is somewhat 10 volts, and the trigger of the different energy and dose has been reduced to further 6 or 8 volts. Similarly, the implants, if we carried out at the N-tap region, the diode which is forming in the parallel to PNP, and similarly with the previous case, it supports the bias connection, the bias potential at base emitter of PNP. So as the equation as the previous suggests, here the VD is always VBA is contributing plus the diode potential and the rest of the equation with the current conduction. Right. So similarly, in the previous case, the base current has been lowered here, and for the same the resistance, P-well resistance, it could be at the lower trigger voltage and the lower trigger current. Right. As a contour suggests that in the previous case the cathode was vanished, and here the anode was vanished to get the lower resistive or the higher conductive part across the region. So that is came. For the results that here the trigger voltage has also been reduced without much change in the holding voltage. Now the tunability, as you see, of the trigger voltage is depending on the few of the energy and the implants. Like the energy here is 35 kiloelectron volts, and further there has been reduced to 30 or 42. And the doping of the implants such that the doping cannot be higher than the normal source drain implants. Right. So this came up with the the proposed configuration, and that is the implants across the cathode region. And then similarly with the P-tap or N-tap implants, there's the N-tap N plus implants over beneath the P plus implants cannot be higher in the doping concentration, can be higher in the energy, which fabrication allows to do. So the diode this time is forming in the series with the NPN junction. Now, for the equation perspective, you can always see that the base emitter has been a negative effect on the beta. Beta, that is the current, the emitter, the current, what do you say, the reverse saturation current belonging supports the beta value. So if you have that the beta value lower than the compared to the conventional one, you have the higher conduction current need to be flown through the device. As you see the contours of that device, the conventional device has already been vanished at the same current density. Now here the cathode has not been vanished. That means higher holding voltage or higher holding current would be required to vanish this electric field present in between cathode and the implants. Right. So here the results has been came out. The holding voltage has been increased from compared to the conventional one. Right. So the tunability is the key factor or the extra factor depending upon the energy and the dose is being carried out, where the N plus lower dose implants have been changing in this particular case. Similarly, as the cathode, there is implant on the anode side, and the results you have seen that the multiple tunability of holding and trigger voltage has been carried out. Now the physics of this concept has been same and also been applicable for the lower voltage trigger or LDMOS SCR. Right. So we are agree upon this that the introduction of the diode, PN diode over the different region can actually change the parameter of different for the different application, and that is holding voltage for the base emitter of PNP, either NPN. You can change the holding voltage, or the trigger voltage you can change according as for the introduction of PN junction over the in parallel of base emitter of both NPN and PNP. Right. So further, the proposed structure has been, the architecture and design has been carried out such that the implants has been alternatively varied in the N-well and P-well region. So there is demand of junction over the region to manipulate the bipolar efficiency of PNP and NPN, and thus the regenerative feedback mechanism has been carried out to change those parameters, either it is a holding voltage or it is a trigger voltage. Now here is some interesting results such that the overall capacitance of the device has been reduced, because of which the turn-on time of the device has been increased, and the DC leakage of the device has tremendously decreased. So these three are the extra benefits of this device. Not only with the shrunken window of the ESD, we can also implants in the multiple or the codependent implants of any device, like it is SCR or any device which is working on a PNP and NPN feedback mechanism. So here the multiple implants of at the P-tap, anode and N-tap has been carried out. Now the various combination can be possible to form basically to achieve that particular holding voltage and trigger voltage for the particular application. Suppose if the device have the particular application of holding voltage 3 volts and the trigger voltage of 8 volts, we can achieve by only defining the doping concentration in different region. We don't have to change the physical dimension of the device. So it is a concept that is not only applicable on the SCR device, it is applicable on the LVT SCR, as I said, LDMOS SCR. That is a case of power clamps, and it can be introduced. The implants can be introduced in multiple window for achieving those kind of characteristics. Now, the one thing that has been drawbacks this device, not the drawback but is a showstopper, and that is the increasing of the trigger voltage. Now, the feedback mechanism working such that it creates disrupt or the early turn on of the NPN and PNP. If you want to turn on NPN, that is create a regenerative feedback mechanism and can create early trigger the PNP turn on. Right. So for that, RC trigger circuit has been implemented with the help of the fellow PhD Mitesh Goyal, and he implemented this RC trigger over this region. So this was kind of a collaborative work further to present in the journal paper and the other conferences. Right. So for the trigger voltage, if we applied the RC trigger voltage over this region, then the trigger voltage has also been reduced. Now this kind of holding voltage has not even been proposed yet, and the highly demand in the industry to get the tunability depending on the doping concentration only. Now tunability is only depending on the device dimension, and the other key parameters has been affected if you want to implement for the one particular application. Right. So here I have concluded my talk for the ESD implant. We have proposed a new structure that can reduce the holding voltage up to 2 diode potential and can go up to the junction breakdown voltages. And we implemented the RC trigger circuit over the SCR to decrease the trigger voltage, and proposed the novel concept to only depending on the doping concentration you can achieve ultimate tunability from as low as to 2 volts to up to the 10 volts. Now one slide I have also put that the mistake that I got and the wrong hypothesis I proposed earlier, and that is we proposed for the different field plate over the trench to modulating the electric field. I came up with this interesting idea of field plate, and by mistake I put the the polysilicon over here in place of metal for the different work function for 4.2 or 4.3 work function. So this idea has been introduced for in the lower, such that the fabrication could be possible. Right. So that's all from my side. Thank you.
So thanks for the wonderful presentation, ma'am. So in the interest of time, we can have one question.
Yeah, I'll ask one question. So fun. All right. You're in third year, right?
Yes, sir.
So you use this doping, right?
Yes.
The last slide. How you know how much doping is done? For example, if I say that I have doped 1 micron of boron to make a P well,
Yes.
how would you know it is 1 micron?
So this is a well-calibrated structure as the Samsung, the South Korea foundry.
I do understand everything. Yeah, everything is commercially imported, right? So let's start with that. That doesn't mean that you should not know, right? If you buy something, how would you know? If somebody says it's 1 micron, somebody says 200 nanometer, then it's a blind belief what we are doing. If I ask you how you would know, so what is the technique to know?
The doping concentration is actually this is only the energy dependent implants. If the energy is high, the doping can be same or the lower. So 10% can be the number.
I don't get the answer to what I'm asking. You can say I don't know. That can be answer, right? That's fine. You cannot know everything. I don't know everything, right? It's fine. But what you are answering is something which is different than my question. My question is very simple. I give you a silicon wafer, and I say that I have P well in your N-type silicon wafer. The P well, the doping, the amount of doping that I have done, will create 1 micron depth. Okay, till 1 micron, you will find out whatever doping concentration may be. 10 to the power 18 per centimeter cube, whatever you want, right? You are purchasing from me. We do some analysis, right? That here, how it is 1 micron? It can be 900 nanometer, it can be 800 nanometer. What is the characterization technique to understand the doping depth?
No, sir, that characterization.
No problem. So that is called SIMS, okay? Surface and mass spectroscopy. So when you take the wafer, we should know. I'm not saying you should be an expert in that. How it is done, how you are using it. Now, if I want you to dope the same wafer, if I give you silicon wafer, right, and I also give you oxide layer, pattern oxide layer, such that you can have only silicon where you want to dope. Which technique you will use to dope the P-type or N-type? What's the doping technique they use to dope your material?
There is impurity.
Dopant is impurities.
Yeah. No, so technical, I don't know the fabrication.
So my advice, I will not be advisor, but still my advice to you is, it is important to understand this technique even we buy things from outside, right? So ion implantation or diffusion, right? One of the technique. Now if you say ion implantation or if you say diffusion, my next question will be which one is better? Right? Yes. So just when you go into deeper and deeper, you will understand that what techniques people use, why it is important. Do we have ion implantation here in our IISc, or we have diffusion? If diffusion, what are the steps of diffusion, pre-deposition and driving? If ion implantation, how we are doing implantation? Right? Those things will help you to understand the things a little bit better. This is my 2 cents. One cost is way more than 2 cents. That's how the English is. Right? So thank you very much, and then keep on doing more research.
Thank you, sir.